space. This n can be very large. Okay, yeah. With the probability distribution W. Okay. So so this is a high dimensional space. Okay, in general. Okay. So the Metropolis algorithm is generally a sequence of points. Okay. So initially, given any initial configuration, okay, x1, okay, and then the Metropolis algorithm would generate another configuration x2, okay, and so on. And then later, okay, as the simulation goes on, then the probability of getting, say, for example, xn or for very large n or sufficiently large n, okay, then the distribution, okay, of this xn after it is formalized, then it will obey your decided probability distribution. Yeah. So,
wow.
So the root is quite simple. Now, so at each point of xn, okay, then I have to make a new trial step. Okay, this trial step is generated at random, but uniformly within the neighborhood of xn. Okay, so yeah, so xt. Okay, this trial step. Okay, this trial step means this is a this is the trial test. Okay, just a trial step. Okay, trial configuration. Okay, you can say it. And this trial step, okay, should not be too far away from the point xn. Otherwise, okay, it's very likely to be rejected. So it has to be at random, but uniformly within the neighborhood of xn. Okay, and the size of the neighborhood, okay, is up to your choice. Okay, yeah, if you make the neighborhood too large, then it's quite powerful. Xn is quite xt is quite different from xn, and then the wave function, the ratio of the wave function, okay, will be very small. So eta is a random number. Okay, so if this ratio is too small, okay, then the chance of being bigger than this random number, okay, is very low. So the acceptance rate is very low. Okay, so this trial step xt accepted as the xn plus 1. Okay, so then you will go to change from the configuration xn to xn plus 1. Okay, if this condition is satisfied. So this condition is computed by the probability distribution of using the new configuration, and then divided by the probability distribution of the old one. Okay, so this is the probability distribution of the old configuration. Okay. So the old configuration means whatever the initial this point xn, then you can use it to compute this probability distribution. Okay, W, or I call it wave function. Okay, whatever you like. Okay. Then after you compute this ratio, then you generate a random number eta, and this eta is a random number uniformly distributed in the interval 0 and 1. Okay, and this number is a random number, so eta could be bigger than this ratio or less than this ratio. So this is not a deterministic process, so it's called stochastic. Okay. Okay, you see, yeah, this number you compute is according to the trial configuration, and the trial configuration is generated randomly. Okay, but say the uniformly within the label of xn. Okay, yeah, and also this eta is a random number. Okay, so whether trial step is accepted or not, okay, you do not know it in advance. Okay, and there's no way you can predict whether it will be accepted or not. Okay, so it is called stochastic. Okay, so if such a condition is satisfied, so if this ratio, okay, is bigger than this eta, the random number generated, okay, then the child's configuration is accepted to be a new configuration in the sequence. Okay. Okay. So that means, yeah. So this algorithm just keep on from one step to another step using the same algorithm, and so on. Okay. So this two lines here, okay, can be written as the one single line. Okay. So this acceptance probability xn to xt is equal to minimum one of this ratio. Okay. So the probability cannot be bigger than one. Okay. So the probability at most is the one. Okay. But yeah, if this ratio is less than one, then that is the probability. Okay. Otherwise, okay, if this is bigger than this, then it's bigger than one. Then bigger than one must be bigger than eta. So it must be accepted. Okay. So this one single line, okay, is a theoretical expression for the acceptance probability, okay, or probability of acceptance of the transition from xn to xt. Okay. So xt, okay, is the successive configuration in the sequence of the simulation. Okay. So is this algorithm okay? Any question about the Metropolis algorithm? Is it well understood now? Hmm? Yeah. So it's very supposed to be quite straightforward and simple. Okay. Yeah. Okay. Now, in fact, okay, this Metropolis algorithm, okay, is one of the particular algorithm, okay, satisfy this detailed balance. Okay. So yeah, in general, any algorithm with the T is the child probability. Okay, so that means X go to Y. Okay, so this is the child configuration. Okay, and this is the acceptance probability. So this is the probability of generating this configuration Y. Okay, so let me go back here. Okay, so this is the first thing is to generate a new child step. Okay, so when you generate the child step, so this configuration being generated, okay, is depends on some probability, okay, because it's generated at random and uniformly within the label of Xn. Okay, so there's a probability of being this child, okay, this new child configuration, okay, is generated, and then another is this new this new configuration, okay, is being accepted. Okay, so satisfy this detailed balance is that, okay, T x go to Y times the A acceptance Y go to X. Okay, yeah, is equal to Wx. Okay, yeah, yeah, and then let's see, yeah. Yes, you see, this is the Y go to X, and this A is the Y go to X. Okay, and this is the X go to Y, and then this X go to Y. Okay, so this is the generating the new configuration Y. Okay, the probability, and then this is the acceptance probability. Okay, X go to Y. Okay, and this is the proportional to the WY. Okay, and this is to proportional to Wx. Okay, so their ratio is the same. The ratio is equal. Okay, so yeah, so this is called the detailed balance. Okay, yeah, any algorithm satisfy the detailed balance, and then it would eventually go to the equilibrium distribution Wx. Okay, Yeah. However, we require the algorithm that is efficient computation. Acceptance probability is high, and also the correlation between successive configuration is very big. Okay. So this is the criteria, say, for the good algorithm or not. Okay. But any algorithm satisfy the DT variance will eventually lead to the equilibrium distribution Wx. Okay. And for the Metropolis algorithm, the way to generate the trial step, okay, is the same, no matter is at x or and y. Okay. So that means x go to y. This probability is the same as the y go to x. Okay. So this trial step, generating the trial step, okay, this is the probability. So because I always use the same algorithm, okay, says the label is always the same, okay. Yeah, no matter I am in at this what was this point xn, okay, then I always generate the with the same neighborhood size of the neighborhood, okay. Yeah, and also generate the xt randomly, okay. So the probability is always the same, okay. Yeah. So this t, okay, is the same, independent of which configuration you are at, okay. And then the acceptance probability is this, okay. So so you can see, okay, the ratio of the acceptance probability should equal to the Wx over Wy, okay. So we can check this. Yeah. Yeah. You can see, okay. Yeah, if Wy bigger than Wx, okay, then this is bigger than 1. So it must be accepted. So A go to Y, okay, is equal to 1. Okay. So this A x go to Y is equal to 1. Okay. So the now if I review, okay, if the Y go to X, okay, would be equal to Wx over Y. Okay, because if I have the reverse it, okay, Y over X, okay, that means Wx over Wy, and then it will be less than 1. Okay. So the acceptance probability will be Wx over Wy. Okay. So you can see, okay, yeah, this acceptance probability, okay, of the metropolis is satisfied the DT balance, okay, because these are equal, so they cancel. And then the ratio of these two, okay, is exactly the same as the Wx over Wy. No matter Wx bigger than Wy or Wy bigger than Wx, okay. So this equality is always true. Okay. Yeah. Yeah, you can check this very easily. Okay, as I already checked it. Okay. Yeah. So any question about this?
Professor.
Yes.
What is
Yes.
T?
T is the sampling probability. Okay. You see, I sample at the point Y, I sample the X. Okay. So this is as the trial step. Okay. As here, the step here. Okay. I have the point at xt, and then I sample a trial step xt. Okay. Okay. So the probability of generating the xt is called the t of the xn go to xt. Okay. Is it clear?
Okay. Thank
So
you.
at each point, you have to generate this point first. Okay. And then the probability of getting this point. Okay. Yeah. You see, because it's generating randomly. Okay. But uniform within the neighborhood of xn. Okay. So there must be some probability, right? Yeah. So not necessarily you will go to this point, you will go to another point. Okay. So another trial configuration will be generated. Okay. So each trial probability, each trial configuration has a different probability. Okay. So So that's the why I have this T. Okay, yeah. But since I do it the same for every point, okay. So for the metropolis, okay, yeah, this sampling probability. So the sampling Y from X, okay, or sampling X from Y, sampling X from at the point Y, okay, yeah, must be the same, okay, because it's a universal no matter at which point. I always use the same sampling algorithm to sample the child configuration. Okay, yeah. I hope now it's clear. Okay.
Okay, thank you.
Okay. Let's see. I don't know why this is the. I thought this has been updated because the date here is not quite right. Okay. Anyway, yeah, I will correct that the day later. Okay. Yeah. Yeah. But the metropolis algorithm has some drawbacks. Okay. Yeah. And because the probability of accepting a new configuration is very small unless the new one is very close to the old one. Okay. Yeah. So the xt, okay, should be not too different from the xn. Otherwise, okay, the w, okay, the w, okay. So if the y, okay, is too different from the x, okay, then the ratio, okay, wy and wx, okay, will be very different. Okay, so here, okay, so if the xt is very far away from the xn, okay, then very likely that w, okay, this okay is quite smaller than this, okay, and then this will be a very small number, okay, and then is the chance of being bigger than the eta will be small, okay. Eta is a number, uniform number distributed between 0 and 1, okay. So so that means xt has to be very close to xn. So that means this sequence, okay, is a correlated configurations, okay, because the new configuration is not generated completely randomly, okay, but depends on the old configuration, okay. Yeah, so this is not a so there's a correlation between this succession of the configurations, okay. Yeah. So there's a very strong correlated sequence of configuration, okay. So that means it will take a very long time to go to it takes a very long time to sample all possible statistically independent configurations, okay. So there's the very long relaxation in correlation times, okay? And this becomes a very serious problem, especially in for a condensed matter system, okay. Yeah, if I want to do a simulation of a condensed matter system and try to simulate its phase transition, then this will be quite challenging for the metropolis algorithm. Yeah, because the configuration so because the correlation length, okay, at the phase transition point becomes infinite, okay. So for finite size system, okay, then it's as big as the lattice, okay. So it takes a very long time to generate a new configuration, okay. Yeah, I mean a completely independent configuration, okay. Yeah, not new, okay. You can generate a new configuration, but this new configuration is have a strong correlation to the old one. So that means you are not sampling all the possible phase space, okay. Yeah. And that means it takes a long time to do the simulation. And this is called the critical slowdown. Yeah. Of course, okay, if you are working on some simple problem, small size problem, and also not at the phase transition point, okay, then you won't encounter such a critical slowdown problem. Okay? Yeah. But I have to mention this, okay, because you think you can use this algorithm to do the large scale simulation, and especially for the condensed matter system at the critical point, okay, then you will encounter such a difficulty if you use the Metropolis algorithm. Okay. Yeah. But for this class, okay, it's a good starting point, and is the basic algorithm, okay, and there are some more advanced algorithms, okay, but they have to more or less some variations from it and the improvement on this Metropolis algorithm. Okay. Yeah. So the Metropolis algorithm generate a sequence, okay, with the probability distribution function Wx, okay. So suppose I have the instead of the high dimensional configuration, say I just use the number, okay, and this number is between 0 and 1, okay. So I want to generate a sequence of this number, okay, and satisfy this distribution Wx, okay. Then what should I do? Okay. So this is the algorithm. This is the steps, okay. Yeah. Initially, just generate a random called XO, okay. Yeah, with the uniform deviate, okay. Yeah, and this is just generate randomly, okay. So, and then compute the WO, okay. Yeah, because Wx, okay, some distribution function, okay, and then I can use it since you have XO, then I can compute WO, and then set I equal to 0, okay. And then now I generate a new random variable x new, okay. Yeah, and then compute the W new, okay, just plug into the function Wx using the x new, and then I get a W new, okay. So if W new is bigger than WO, then I accept the x new, okay. So this x new will be the next x in the sequence, okay, and then set XO to x new, and then WO to W new, okay. So this is for the code, okay. Yeah, such that you always have the XO and x new, okay, only two sets of variables, okay. Yeah, and otherwise generate random number R, okay, with uniform deviate. And then if the R less than the W new over WO, then accept the x new. And again set this, okay. After that, then I set the xi, okay, equal to xo, and then I go to I plus 1. Okay, so this is the pseudo code, okay, to of the Metropolis algorithm to generate a sequence, satisfy a distribution Wx, okay. Yeah. So if x new is rejected, then XO is saved in the sequence, okay. Yeah. So you see, this is push XO, always push XO to the sequence, okay. Yeah. And here, yeah, if accepted, okay, XO will equal to x new. That means x new is goes to the new configuration, new number in this sequence, okay. If it's not accepted, okay, then I still have this XO is the same XO, okay. But then I still have to put it accept it, put it as a configuration on the sequence. That means in the sequence, okay, I can have two successive number are the same, okay. If it's not accepted, then the number in the sequence, okay, still is the XO, okay. If we accepted twice, then there will be 3 XO in the sequence, okay. You see? Yeah, you must have to put the XO in the sequence, okay, you do not put the XO in the sequence, okay, then your distribution WX, okay, would not be correct, okay, yeah. So this is one of the important points in doing the Metropolis, using the Metropolis algorithm to generate a sequence of X, okay, satisfy the distribution WX, okay, yeah. Many people, okay, especially this new new users, okay, yeah, they come to the when they write a code, okay, using the Metropolis algorithm to generate the sequence, okay, they often just if it's rejected, then just throw away, okay, not save it to the sequence, and that's wrong, okay, yeah. So that means whenever you generate a configuration, okay, yeah, if you accept it, then you put the new one on the sequence. If you reject it, then the old one will be kept on the sequence and move to I plus 1. Okay. So now, since I want to generate endpoints, so if I is less than n, then I go to this step and then repeat this. Okay. Okay. Is the algorithm here? Okay. Yeah, this step is important. So I use red line here. Okay, to emphasize this. Okay, because the new user, okay, usually makes this incorrect. Okay, once it's rejected, then just throw away. Then the sequence will be wrong. Will not satisfy the WX. Okay. Okay. So so this is the code. Okay. So this is pseudo code. Okay. Yeah. So XO equal to the so this is the GSL, okay, random number generator, uniform random number generator, okay, RNG, okay. So which random number generator you use? Yeah, you depends on what pointer you are linked to. Okay. So first generate XO, and then I compute the WO. Okay. Then for this for loop here, okay, and then I start with the X new, okay, generate X new, and then compute the W new, okay, with X new. So if the W new is bigger or equal to WO, then I accept it, okay, accept the W new. So I update the WO to W new and the XO to update it to X new, okay, yeah. And then here I push the XO, okay, to the sequence, okay, yeah, yeah, yeah. So if W new, okay, is less than WO, okay, then I have to generate a random number out, and then to check this ratio, whether this ratio W new over WO is less than R. If yes, then the WO equal to W new, XO equal to X new, okay, that means C is accepted, okay. Yeah, if R less than this ratio, then the X new will be accepted. So I push it to the update the WO and XO, and then XO. That means if it's accepted, then the X new, okay, will be put on this array, okay, as a new entry, okay, in the sequence, okay. However, if this is not true, then the original XO, okay, will still be, okay, saved in the sequence, okay. So yeah, if X is rejected, XO is saved in the sequence, right? Yeah. So this is exactly the why this step here, okay. Yeah. If it's rejected, then XO is saved in the sequence. Okay. Yeah. Yeah. So this code, okay, this pseudo code, okay. guarantee the metropolis algorithms implemented correctly. Okay, yeah. Any question about this? Yeah.
Hi, Professor. So just
Yes.
one quick question for understanding.
Yes.
So
Yeah.
for instance, I see that the algorithm tends to favor the data point with larger weight. So, for example,
Yes. Yes.
if the weight function is a parabola facing downward, then it looks like that. The algorithm will sample much more near the local maximum. So is this also a kind of expected property with
Yes.
this algorithm?
Yes. Sure. It's always the case. Okay, because when you have the higher probability, that means these points are more important. Okay, so this configuration is more important. So that means these points will make the contribution, okay, to the integral, okay, more in contribution to the integral, right?
Okay,
So,
okay. That point will be sampled much frequently.
Yeah, much more frequent than the other with a small w, okay, x, okay, yeah.
Okay,
yeah.
Okay, I see. Thanks.
Yeah. You see, when I talk about the Monte Carlo simulation in the beginning, okay, here, okay. Yeah, suppose this is the w, okay.
Yes.
So you see, if this is you see there are many configurations, okay, and the some configuration give me a larger weight here, okay, larger probability here, okay. So I sample this configuration more often, okay, than other with configuration give me a small probability, probability, okay, small weight, okay, small weight, okay. So you see, in doing this, okay, this factor already embedded in the sampling, okay, you see. So
yes.
Here I don't need this factor come in here at all, okay. Yeah, you see, so important sampling, that means I sample the configuration with if it's a higher probability, I have if this give me higher probability, then I will have a more, I will sample these points with a higher probability, okay. If this configuration give me a smaller probability, then it will be less frequently sampled, okay, not so frequent sampled, okay. So that's reason why I can omit this factor, okay, in this summation here, okay. Yeah. So
okay, then I have a subsequent question. So
yes.
for instance, if the PDF of the weight function has multiple local maxima, in that case, might there be any problem because the algorithm might be trapped at a certain
Yeah. So this is the one of the problem, okay. So you have to your algorithm presumably has to be sample all the maximums, okay. Yeah, if it's the equal probability, okay, you will not be trapped in one of the maximum, okay. Yeah.
Okay. Thanks.
Yeah. Yeah, this is always not as easy, okay, when there's a many, especially there are many maximums, okay. Yeah. And also they are at a different scale, okay. Yeah. You see, the difficulty is the trial step, okay. If you make the trial step, okay, you see if you have a two maximum, okay, it's quite far apart, okay. then it's hard to sample, okay, correctly, okay. Yeah, if this child step, okay, if might make the label too large, okay, then it will be the XT, okay, generated will be quite little probability being accepted, okay, yeah. But it could still possible, okay, yeah, gradually, okay, yeah, it will go to one maximum to another maximum, okay, yeah, but yeah, so yeah, Metro's algorithm is not very good, okay, in dealing with such a situation, actually, yeah.
Okay.
There are better algorithms of doing that, okay, yeah.
Mm.
Yeah. Yeah, if you are looking, say, for example, this Boltzmann distribution, okay, it's okay, okay, because it does have this multiple local maximum, okay. Yeah, but if you are having some, for example, this special energy function, okay, yeah, is has a multiple maximum, or yeah, then it would be challenging for the Metropolis algorithm.
Okay, thanks.
Okay. So now let me go on to talk about the Ising model. Okay. So this is one of the most important model. Okay, in physics, in mathematics, in engineering. Okay, yeah, it has very wide impact. Okay, even though it's very simple one model. Okay, so there's a description of the Ising model in Wikipedia. Okay,
Simple.
yeah, I think it's
Very hard to solve.
quite well written. Okay, so now consider spins on a d-dimensional lattice in general. Okay, yeah, yeah, and this lattice is a torus. Okay, because you are imposed a periodic bounding condition, then it's similar to a torus. Okay, so for one-dimensional lattice. Okay, then I impose a periodic bounding condition, then it is a circle. Okay, so for two-dimensional lattice, okay, then it would look like the torus. Okay, yeah, and high dimensional, d-dimensional, then this is the high dimensional torus. Okay, yeah, and yeah, and then the energy, okay, is computed in by this expression. Okay, yeah, say each side, okay, only have the two different value. Okay, spin up or spin down. Okay, +1 or -1. Okay, yeah, and the interaction, okay, interaction energy is only Lear's label interaction. Okay, yeah, there's no next to Lear's label interaction. Okay, and the strength is a J coupling strength. Okay, and then you can also have an external magnetic field B. Okay, so the interaction between the magnetic field and the spin, okay, is B times sigma. Okay, sigma I. And since I have many spins, so I have to sum over all the spin interaction with the external magnetic field. Okay, and presumably this B field is a uniform. Okay, otherwise B is a function of I. Okay, yeah. Yeah. So the sigma I is just a psi index. Okay, yeah. Suppose have a integers. Okay, the coordinates. Okay, I1, I2 to IT. Okay, yeah. Okay. Now, I can write the partition function. Okay? Yeah, exponential minus E of sigma over KT. And then sigma is a spin configuration. Okay, yeah, the correction of the spin sigma I. Okay, sigma I can be +1 or -1. Okay, when you have the entire lattice. Okay, then you have say, yeah, this is the yeah, many spins. Okay, so yeah, even one spin are different, then it regard as a different configuration. Okay, yeah, yeah. So some of the configurations. Okay, so you have an n size. Okay, the number of configurations 2 to the power n. Okay, yeah. And here is the sum over all the configuration. And each configuration, you have an energy, E of sigma. Okay. And over the KT, K is the Boltzmann constant, T is the temperature. So sum over all the probability of over all the configuration, spin configuration, and then we call this partition function. Yeah. So I can write this as this exponential of the K sum over sigma I, sigma J, okay, and then sum over all the release labor, and then plus H times as sum of sigma I, okay. And here we define the constant, okay. The K, capital K is the J over KT, yeah. H is the B over KT, okay? Yeah. So in statistical mechanics, partition function is the most fundamental quantity, okay. If you can evaluate the partition function, then we can obtain all statistical properties of the system, okay. For example, the magnetization density, okay. So the sum of all the spin, okay, of the system divided by the number of sites, okay. So that means the average spin per site, okay. Yeah. So this is magnetization density, okay. And this can be obtained. So this is the formula, okay. I can write because each spin configuration, okay, has a probability, okay, E minus E sigma over KT, okay. So this, and then the sum over all the spin configurations, okay. And this is divided by 1 over 3, okay. Just the normalization, okay. Yeah. So this can be obtained by differentiation of the log D over with respect to H. Okay, you can see, okay. Yeah. When you perform the differentiation, you get 1 over D, and then when you have the differentiate on the exponential, then you bring down the factor sigma or sum of sigma I. Okay, so you obtain this. So you get this expression. So if you know D exactly, then you can do this differentiation. You know this analytically, okay? Then you can do the differentiation, and then you can get the magnetization density. Okay. Similarly, for the energy density, E sigma. Yeah, you can obtain it by taking the derivative with respect to K on the log D, and then minus of the B times the magnetization density. Okay. So this is easy to derive. Okay. Yeah. So just tell you the partition function is the most fundamental quantity. Okay. So if you can evaluate the partition function, everything else, okay, can be obtained. Okay? But too bad the partition function is very difficult to evaluate. Okay. Yeah, even for the Ising model, okay, except one-dimensional Ising model is very easy. Okay. Yeah, you can obtain the partition function one-dimensional. Yeah, one-dimensional Ising model. Okay. Actually, that was the PhD thesis of Ising. Okay, back in 1925. I don't know. I forget. Yeah, you can look up the Wikipedia. Okay. Yeah, but then the two-dimensional Ising model, takes a long time to obtain the partition function. Okay, the first answer, okay, was the Onsaka. Okay, that was around 1940 something. Okay. Yeah, but the paper was very, very long and a lot of mathematics. Okay, a lot of people could not understand it. Okay. Yeah, and also there's a Chien-Yang. Okay, yeah, he also get a magnetization. Okay, analytically. Okay, and yeah, without the magnetic field. Okay, without the magnetic field. So without the external magnetic field, the magnetization. Okay, yeah. That was in 1952, I think. Yeah. Yeah. And then there are many exact solutions in the statistical material system. Okay, but for the three-dimensional Ising model, so far we don't have an exact solution of the partition function or any other quantities. Okay, so people tend to think, okay, yeah, exact solution for the three-dimensional Ising model is impossible. Okay, so until someone can work this out. Okay, so I don't know whether it will be obtained or not. Okay, in the future. But we can always do the simulation, Monte-Carlo simulation, to obtain the answer. Okay, but there's not an analytic answer. Okay, it's a numerical solution. Okay, so the numerical solution always just give you an insight to a system. Okay, and yeah, it could be the realistic physical system. Okay, you can simulate. Okay, yeah, the analytic solution, all this, okay, sometimes have to do some simplification, okay, and approximation. Okay, so otherwise it's hard to get the analytic solution. Yeah. So let me consider this two-dimensional lattice, okay, with the periodic quantum condition. Okay. So this two-dimensional lattice with periodic quantum condition is equivalent to a torus. Okay. You can see, okay, yeah, the point here, okay, actually is identified as the point here. Okay. So similarly, the point here is identified as a point here. Okay. So yeah. And the site here on the boundary here, the nearest neighborhood, nearest neighbor, okay, is this three side and also this side, okay, here, okay, yeah. So this is the 10 by 10 lattice. Okay. Now let's look at the Metropolis algorithm for the Monte-Carlo simulation, okay, of the spin systems in general, okay, yeah. So I will go to each side and generate a new spin, okay. So this is the T, okay, this for arbitrary probability distribution satisfy this, okay. Okay. So at I, you can generate the sigma I is the same probability as you have the sigma I would give you the sigma I pi give you the sigma I. Okay, so yeah. So this T, okay, many ways you can generate the sigma I pi, okay, satisfy this, okay. For example, if I have the sigma I pi always opposite of to the sigma I, okay, if sigma I is a plus 1, okay, then I select the sigma I pi to be -1, okay, then this way of getting the sigma I pi, okay, satisfy this equality, okay, yeah. So on the other hand, okay, if you can go to the sigma I side and then get a random number, okay. If the random number is a spin is bigger than 1/2, I put the sigma I pi to be a spin up. Otherwise, okay, sigma I pi is a spin down. So this way of getting the sigma I pi is independent of sigma I. Okay. So this also satisfies this equality. Okay. Yeah. So there are many different ways to generate the sigma I pi, but it's very easy to construct one which satisfies this equality. Okay. Yeah. And then compute the change in energy. Okay, delta E. Okay, yeah, this is the using this new spin sigma I, you see that this spin configuration, okay, only at one side, you change the spin at one side, okay? So you only need to compute the energy change due to the sigma I pi changes, okay? So E of sigma I pi minus E of sigma I, okay? So E of sigma I means that this configuration only at the side I, okay, is sigma I pi, okay? And this is the energy of the system with the sigma I at the side I. Yeah. So if the delta E change of energy is less than 0, okay, yeah, that means this one is a new spin configuration with an energy less than the old spin configuration. Then sigma I pi is accepted. Otherwise, generate a random number R between 0 and 1 with uniform delay, and then check whether this R is less or equal to the exponential minus delta E over KT. Then sigma I pi is accepted. Okay, so this is the A of the sigma I go to sigma I pi. Okay, minimum of 1 of the this the new probability, new wave function. Okay, over the old wave function, old W. Okay, W pi and W. Okay, so this is the, because this is the distribution we want to simulate. Okay, we want to simulate the sigma configuration. Okay, satisfy this probability distribution. Okay, so so this is the Metropolis algorithm. Okay, and here is these two ratio. Okay, exactly this the same as the exponential minus delta E over KT. Okay, because you have this minus E sigma pi, and then this come up here becomes plus E sigma. Okay, so it's the same as the minus delta E. Okay, so at each site I do the same thing, do this the same updating. Okay, repeat the same procedure for another spin. Okay, so yeah, if it is not accepted, then the sigma I is the same as before. Okay, yeah, just not changing. Okay, not changing the sigma I pi. Okay, so after go through all the sites, then I complete one swap. Okay, swap. Okay, I have one swap. Okay, and then go through each site again. Okay, then when you complete all the sites, then I have another swap. Okay, so this is the way how the Metropolis algorithm can be used in the updating of in the Monte Carlo simulation of the spin systems in general. Okay, yeah. Any questions? Yeah. Is it quite straightforward? Yeah, I will go to a code, okay, and then you will see more theory. Yeah. Let me this transparency, okay, is a obsolete. This 01, okay. Let me go to a new one. Okay, this is the not what I want to do here. And let me see here. I should go to the 2024. Okay, here. Put up. Okay. Okay. Yeah. So this is the updated. Okay. So this is a using model. Yeah. So the complete code. Okay. Now I only look at the CPU code. Okay. Yeah. So the complete code is in here. Okay. Yeah. You can look at the code. Okay. Yeah. So this two for loop is means go through every side, okay, go through each side, okay. So as side, okay, since I use the one-dimensional array, okay, so I have to convert these two index I1 and J1 to the one-dimensional array, okay. And then so this is the usual way, okay, similar to what we have done in the Laplace equation. Yeah, we put the few variables, okay, on a one-dimensional array, okay. So in this case, the few variable is the spin, okay, and it only has the +1 or -1, okay, rather than a real number. Okay. So the O spin then decide, okay, K, okay, and the O spin is equal to a spin at the side K, okay. And the way I generated sigma I pi is always the negative of the O spin. New spin always negative O spin. Okay. So this is the T I used. Okay. This is the T. Okay. How I select it? How do I select the new spin? Okay. The child spin. Okay. Select the child spin. Okay. Yeah. And this way, every time I do this, okay, at each side I do this, then you will satisfy this equality. Okay. Yeah. Okay, with this new spin sigma K pi. Okay. And then I look, because we don't, it only has the least label interaction. So I only know what are the spin of these labels. Okay. Yeah. So the K1 is the right, K2 is the top, K3 is the left, K4 is bottom. Okay. So this is quite similar to the case of the Laplace equation. Okay. It's four labels. Okay. Yeah. Up, down, left, and right. Okay. Yeah. Again, I have this is forward and backward array. Okay. To take into account of the boundary condition, periodic boundary condition. Okay. Yeah. And then I sum over all the spins, okay, of these labels, okay. So spin of K1, K2, K3, K4, okay. And now I compute the change of energy, delta E, okay. Delta E is minus of the new spin minus old spin times the spin S, okay, sum of the labeling spins, okay, and plus the magnetization B, okay. Now, if the dE, delta E, okay, or less or equal to 0, then it's accepted, okay. Then sigma, the spin K is equal to new spin, okay, accept the new spin, okay. Or I generate random number. Either whenever it see dE is less or equal to 0, then it does not need to compute this expression. Then you go to the acceptance, okay. Now, if this is not if dE is bigger than 0, okay, then you will go to computers. That means you will generate a random number and then test whether this random number is less than the exponential minus dE over t. Okay. Yes, if yes, okay, either this or this is condition or this is satisfied. Okay, either this condition or this condition is satisfied. Then the new spin will be accepted. Okay, the spin at the site K, okay, K with the coordinate I1 and J1 will be accepted. Okay, to be updated to the new spin, accept the new spin. Okay. Otherwise, you will just spin K, okay, is the same as the old spin. Okay, same. Okay, not changed at all. So I have to go through all sides, okay, with the same updating algorithm. Okay, and then if I do many updates, many swaps, then eventually, okay, the spin configuration, okay, will be proportional. The way to I mean, the way to get the configuration will be proportional to the Boltzmann distribution, E minus E sigma over KT. Okay. So that means after a simulation a long time, okay, simulate after go through many swaps, then you reach, it will be thermalized, okay, what we call thermalized. That means after that, then the configuration is sampled will obey the probability distribution, okay, the Boltzmann distribution, E minus E sigma over KT, okay? Once you reach the thermal equilibrium or reach the thermalized distribution, okay, then you can start the measurement, okay? You can start the measurement. You can use the sigma, use the spin configuration to do the measurement of the energy or the spin or magnetization, okay? And then you get the expectation value of the energy and the magnetization, okay? Yeah. So this is the, okay. So after thermalization, the probability of getting a spin configuration is proportional to this, okay? Then the expectation value, any observable, can be measured by averaging over the configurations, okay, you see. So suppose you have to, here, okay, in this expression, you have to sum over all the configurations. But the important sampling tells us, okay, if I sample the sigma, okay, yeah, with satisfy this probability distribution, then I don't have to multiply this, okay, because this probability already embedded in the sampling process, okay? So I can just average it over the configurations, okay? Okay, because the probability of getting this configuration is proportional to this probability. Okay? So this is the important sampling, okay? Yeah. Rather than the simple sampling, or rather than you go through all the configurations. Go through all configurations is possible, okay? Even say 100 sites, okay? 10 by 10 lattice, okay? Then you have to go through 2 to the power 100 configurations, okay? Because each site has a 2 configuration, spin up or spin down, okay? So it's impossible. No matter for what kind of supercomputer you have, you cannot do the summation directly, okay? So the only possible way you can get an answer, get a reliable estimate of the answer, okay, is the Monte Carlo simulation by the important sampling, okay? So if you have a more computing power, you can sample more configurations, and then you get a value, okay, with less error, because the error of this average of this mean value, okay, expectation value, is proportional to 1 over squared m, okay? So if you increase the number of the samplings in the measurement, increase the number of measurements, then your error will become less, okay? So this is the central limit theorem. I already demonstrated this last time with this simple integral, okay? Yeah. Similarly for the magnetization, okay? So this is the in general for any observable. So for magnetization, I have to obtain the expectation value, the sum over the I spin over all size. So so I just have these configurations, and then sum over the average over the configuration of this magnetization, and then I get the answer. Okay, again, the error is proportional to 1 over square m, the number of the measurements. Okay, and the energy density. Okay, so with the Monte Carlo simulation, you can get the expectation value of the observables, okay, with the limited computing resources, okay. Yeah, you get more computing resources. You can get a more accurate answer by doing more measurements, okay, or by making more sampling, okay, sample more configurations, okay. So, Any questions? Yeah. No? Yeah, I hope everyone is clear how's the Monte Carlo simulation works using the Metropolis algorithm on the Ising model. Okay. Yeah. So I go to the sample code and do some demonstration. Okay. Yeah. Let me switch to another screen. Let me stop this screen first and then share another screen. Yeah. I hope the connection is still there. Oh, yes, it's still there. Okay, great. So let me go to the CPU code first. Using 2D CPU. So I have written the detailed documentation on my sample code. Okay. Yeah. I use the GSL, GNU Scientific Library random number generator routines. Okay. So here there's an exact solution, 2D exact solution. Okay. I also need some elliptic functions. Okay. Yeah, and also these functions. Okay. It is at the end of the code. Okay. Yeah. Let me go to the end of the code. Yeah, here. So some function, maximum or minimum function. Okay. And also the elliptic functions. Okay. So these are for the exact solution. Okay. Yeah, it's up to your interest. Okay. Yeah, you want to understand it. Okay. And you can read it carefully. Okay. Yeah. So the exact solution, yeah, is here. Okay. So exact solution 2 model on the infinite lattice. Okay. So this is for infinite lattice, not for finite lattice. Yeah. There's no exact solution for 2D Ising model on the finite lattice. Okay. Yeah. So this is yeah. Yeah, the exact solution you can analytically, yeah, you can look up the Wikipedia, okay, and then you give you the references, okay. Yeah, and from there, okay, you can also write up the numerical routine for computing the exact solution, okay. Yeah, but here I have already implemented, okay. So you can just take for granted, okay. Yeah. Now, let's focus on the algorithm, okay, and on the simulation with the Metropolis algorithm, okay. Yeah. Yeah, the network is a little bit slow because I'm connecting it from United States. Okay, so yeah, actually I have been many different places. So the internet connection yeah, depends on where I stay. So yeah, I'm staying. Okay, so yeah, the Wi-Fi and also the network. Okay, yeah. So yeah, but you can see, okay, the every variable has the document. Okay, yeah, so you know exactly, okay, yeah, what it means. Okay, yeah. Okay, let me first of the in the beginning of simulation, okay, is initialize the random number generators. Okay, yeah, and then I use the machine twister. Okay, 19937. Okay, yeah, you can use any random number generator. Okay, for example, the RAND. Okay, yeah, the one come with the any Linux system. Okay, so yeah, I have to initialize this random number with a seed. Okay, so yeah, whatever the number seed you can enter say 1 2 3 4 5 or so on. Okay, doesn't, yeah, or even 0. Okay, for this case, okay, it works. Okay, but not necessary for any other random number generators. Yeah. So enter the number size in each direction. Okay, so presumably this is a square lattice. Okay, so I only have to enter, say, how many size in one direction. Okay, yeah, then and so I have this array fx and fw and bw is the forward and backward array, taking into account of the periodic binding condition. Okay, so yeah, so for the forward, okay, it's just yeah. So go through each side and then I+1 and then the mode nx. Okay, so when it's yeah bigger than, when you go to nx -1 and then +1, then it will be wrapped around. Okay, is the side 0. Okay, in this direction. Okay, again the backward. Okay, it's -1 plus nx mode nx. Okay, so this is well known. Okay, because we have done this in Laplace. Okay, 2D Laplace equation. Okay, and then the spin. Okay, the spin is a array. Okay, yeah, of the ns size. Okay, ns floating point integers. Okay, yeah, and then the number of swaps for formalization. Okay, and then ended the number of measurements. Okay, yeah, so here I also entered the interval between successive measurements. That means I do so many swaps or updating. Then the next measurement could be another configuration after so many swaps of update. So that means separated by some swaps. Okay, so this is the interval between successive measurements. The reason of doing that is to try to reduce the correlation of the configurations. Okay, yeah, because when it's interval longer, then the correlation supposed to be smaller. Okay, yeah, except in the case of the a critical in the phase transition. Okay, then the correlation will be very long. Okay, infinite. Okay, or as long as the size of the lattice. Then in that case, okay, the intervals has to be very, very large. Okay. Yeah. Okay, and then enter the display interval. Display interval just for this for the when I do the interactively. Okay, then I can see how many swaps then you will display. Okay, the result. Okay, so I can see on the console. Okay, and then the interval for saving the spin configuration. There is the I want to save this spin configuration, because once I have the spin configurations, okay, then I can do the measurements. Okay, yeah, the m. Okay, how many measurement? Okay, the m. Okay, is the, but in order to do the measurement, I need the spin configuration, so I can save these spin configurations and then do the measurements later. Okay, this is necessary, okay, is crucial, okay, for the data analysis, okay, when I want to know what's the correlation, okay, of the configuration or such that the estimated error of the observables property, okay. Yeah, because I cannot regard all the configurations statistically independent. So I have to take into account the correlation of the configurations, and then the error, okay, will have an extra factor due to the correlation of the configurations. Okay, I will discuss this the error estimate later. Okay, yeah, and the temperature is in the unit of JOK. Okay, external magnetizations, and the initial spin configurations, cold start or hot start. Okay. Yeah. So for the cold start means the initially all the spins are spin up. Okay, spin is one cold start. Or hot start is the spin could be randomly between +1 or -1. Okay, so just call a random number bigger than 0.5. I assign +1. Otherwise, as -1 spin down. Okay, so yeah. Also output the spin configuration and also to output the data, okay, the measurement data, okay, or just the output, okay, yeah, or the pinout, okay, yes. Here, so the first I initialize the accumulators for the energy and magnetization, and the total number of swaps, okay, is the number of swaps for thermalization and the number of the swaps from measurement, and then because there's a interval, okay, between the measurements, so the total number of swaps you have to do is this, okay, total, okay, and here is the created timer, okay, yeah, I want to time, okay, how much time, okay, it takes, okay, for the entire simulation, okay. So universally using the CUDA timer, okay. So this code has to run with the with the CUDA, using the CUDA, okay. Yeah, even though you do not use the GPU in this case, okay. Only to use the CPU, okay. Yeah, but it's still working using the CUDA, okay. Okay, here is the go through each site, okay, to do the updating, okay. This I already covered, okay, in my slide, okay. So I go down here, okay. Yeah. So if the swap is bigger than the NT, the number of thermalization swaps, and also the swap is more IM, say how many swaps between the different measurements, okay. So IM, okay, then do the measurement, okay, here, okay. So for the magnetization, I just sum over all spins, okay. And for energy, I also sum over all the go through each site, and then the sum the energy, okay, of this labels, okay. Here I only sum the positive direction, K1 and K2, okay. Yeah, because if I sum 4 bonds, okay, all labels, okay, then it will be overcounted, okay, and you have to normalize it, okay. So if I only sum over the positive direction, then that means this I will go through. That means sum over all the bonds, okay, in the system of the system, okay. Then the energy is energy minus B times magnetization, and then I got the total energy, okay, and then total magnetization, and then count becomes +1, okay, yeah. And then here is the so this is the measurement, okay, for just one measurement, okay, yeah. So and if this display, then you will display how much, okay. So this is the for the this is temporary, okay, just for the visualization, okay, yeah. And then the save, this is for saving the configurations, okay, yeah. And then and finally, okay, yeah, I have this is a pin out after this, then I pin out the exact solution, okay, yeah, together with the this is exact solution, okay, and also yeah uh, yeah, only for b equals 0, then I have the exact solution. If b is not equal to 0, okay, then I don't have the exact solution, okay, yeah. And then get the time, okay, and time the how much time, processing time, and also the gigaflops, okay, yeah. Okay, so this is the CPU code, okay. Now let me see, okay, so I just have the job run that with the CPU here, O1 CPU. Okay, you can see, okay. So this is the measurements, okay. This is the yeah, and this is the exact solution, okay. You see, I have the temperature T is the 2.4, okay, yeah. And then exact solution, you can see the minus 1.2 here, and then this the 1.2, and then, but the magnetization exact solution say 0, okay, but this not exactly 0, okay, because this is finite system first, and also the there's a numerical error, okay, so I cannot have the exact 0, okay, so it's more, but it's not exactly 0, okay. So processing activity CPU is this is incorrect, okay. I don't know why the processing time is incorrect here. Let me see, this is the input for CPU. Right. Oh, okay. Now, let me look at the, okay, input 1 CPU, okay. Huh? Input 1 CPU. Okay. So this is the C, and then the number size 256. Okay, actually this is quite large. Okay, yeah. And the number of swaps is for thermalization is 1,000. Okay, number of measurements is 1,000 measurement, and then the interval between successive measurement is 10, and the display is every 100 swap, then it would display once, okay. And then there's interval for saving the spin configuration is 10, and this is the temperature is the 2.4, okay. So temperature 2.4 is high temperature, okay. Yeah, it's a Yeah, you see, the Ising model has two phases, okay, and there's a phase transition around t is 2.2 something, okay. So 2.4 is in the high temperature phase, and then magnetization 0. And if the temperature T is say less than 2.2, say 2, then the magnetization will be 1. It has the spontaneous magnetization. Okay. Yeah. Okay. So let me try to do this. And using 2T CPU. Okay. Say, let me use 100. Okay. Yeah. Small lattice. And 1,000. 10,000. Okay. 10. 100. Say 2.0, okay. Say 2.0 is below the critical temperature. Yeah, so it's cold start. So you can see it's quite fast, okay. Yeah, because the timer, okay, yeah, I have to use instead of using the cooler timer, okay, I have to use the Linux, okay, CPU timer, system timer, okay. Then you will give me the correct timing, okay. Yeah, I will change it later, okay. But you can see, okay, the exact magnetization is about 0.9, okay. And this give me the 0.91, okay. So it's quite close to the exact solution. And similarly for the energy, okay. So the energy is so the exact solution is presumably for infinite lattice. But then the simulation result, okay, give me the yeah, it's quite compatible to the exact solution, right? Yeah, one part in 1,000 or even better. Okay, yeah. So you can see the power of doing the simulation. Okay, yeah. For such a 100 by 100 data, you're already quite close to the exact solution. But for the high temperature phase, okay, then it does not give me the correct answer, not quite close to the exact solution for the magnetization, because for the infinite lattice, okay, the magnetization is 0, okay, but here I only get say about 10 to minus 3, okay, so it's not exactly 0, okay, so yeah. There are several files, okay, coming, okay, here the spin CPU.dat, okay, yeah, it supposed you see this is the spin configurations, okay, so each row, okay, give me the spin configuration of the entire lattice 100 by 100. So there's a 100 entries on one row, and then the total is is it, let me see how it's arranged. 100 by 100. So so there are 100. There's reason why the number of lines is the 10098. Okay. So this is the 100 column, 100 row, okay, is a one spin configuration, okay? Yeah, and this spin configuration is with 1100 swaps, okay? Each swap has this data is saved here, okay? So with the spin configuration, you can read this spin configuration and then do the measurement again, okay? Yeah, and then do the proper error estimate. Yeah. Yeah, there's another simulation is using the GPU, okay, using one GPU, okay. So, but I don't think I have enough time to cover the simulation with the GPU, okay. So, but anyway, do you have any questions, okay, on the using the CPU code, the CPU code of the Monte Carlo simulation of two-dimensional Ising model? Yeah. Any questions? Yeah. You can submit the this G1 here. Yeah. Yeah, I have these three arguments. Okay, this is for the CPU. Okay, and this is for the GPU, and then GPU with the global memory version 1, and there's a version 2. Okay, and then each of them has its own output. Okay. Yeah. Yeah. Later, I will update the CPU code such that the timing, okay, will, instead of using the NVIDIA timer, okay, CUDA timer, okay, I will use the CPU timer, okay. But I just don't quite clear why in this case it doesn't work. Anyway, I will fix it, okay. Yeah. Presumably, this CUDA timer should also work, even for the CPU code, okay. But there must be some problem of the system or about the code, okay. I remember before, okay, this CPU code works, okay. I mean, the timing is working properly. Okay, so, yeah. Okay. Yeah, about the GPU implementation. Okay, let me go to the GPU implementation. Okay, before I skip this. Okay, and then I go to the another screen. Okay, the actual one. Okay, yeah, and then go to the CUDA 9. Okay, here. So yeah, this is the GPU accelerated Monte Carlo simulation. Okay, using the global memory. Okay, and also I will using the constant memory to enhance this speed. Okay, and then the error estimate. Okay, but I don't think I have the time to cover everything here. But at least I think I can cover some of it. Yeah, suppose I have the lattice size 16 by 16. Okay, yeah. So you can see there's this 16 by 16 lattice. Okay. If I cut this lattice into grids, okay. Excuse me. So each grid dimension is the 4x4, and let me see. Yeah. I think this is the other one. Let me go to. Yeah. I think the other one is the for the okay. This one already known. Okay. So now. So the question is how to perform parallel updating simulation with the Metropolis algorithm. Okay. Yeah, because for the CUDA, okay, I have many threads, and then I have to using the block, okay, and the threads, okay, to do the computation. Okay. So but because the updating is a list label, okay, so I cannot have every thread, okay, update the each site, okay, together, okay. Even I have the one block, okay. Now if this two threads, okay, are working on the neighboring sites, okay, then the information, okay, of this neighboring spin, okay, is not well defined, okay, depends on who is updating first, okay. Yes. So I have to come up with another algorithm, a scheme, okay, such that I can avoid the updating of neighboring spins at the same time, okay. So one way is to use the even odd or scheme, okay. So this even odd scheme is the group the larger size into two sets, okay, and the even size and odd size, okay, and the neighboring size of any even site and the odd size and vice versa. So if I update the even size, okay, then the odd size are stationary, okay, static, okay, not updated at all, okay. So that means all the even size or odd size can be updated in parallel. Okay. So for example, the update can be first performed on all even size in parallel, and then go on to the update all the odd size in parallel, and then this will complete one swaps. Okay. Of course, you can see this even odd scheme, okay, only works for the model with the list labels coupling, okay. Yeah, if it has a more than just list label, okay, next to list label, okay, then even odd scheme has to be revised such that it can work for such a system with the next to list label coupling. Okay. So the main point is that, okay, when you do the updating, okay, in parallel, then you cannot update two spins, okay, they have the interactions, okay. Otherwise, okay, you do not know what's the spin of these labels, okay. Yeah, depends on which thread, okay, complete the is updating first, okay. So, and then you'll be come to, yeah, into ambiguous situation, okay. So for the even odd scheme is this, okay. Suppose I have the 4x4 lattice from 0, 1, 2, 3, and then 15, okay. And then this is the even size, okay. This circle, red circles are even size, okay. And then this green cross are the odd size, okay. So the idea is, I mean, to relabel it, okay, to get the even size and the odd size, okay. Yeah. So for the odd, here the even size, okay, red one, okay, 0, 2, 5, 7, 8, 10, 13, 15. Okay. So this is the even size. Okay. 0, 0. Okay. And then this is the odd size. Okay. Here. So to produce the even size, okay, then I have to map the even space to the full space. Okay. So IE, okay, is the index for the even size index. Okay. Yeah. And then the X and Y is in this entire lattice. So this is the, okay, yeah. So if I have this numbers, okay, 0, 0, 0, 1, 1, 2, 4, okay. Then for the even side, okay, I will have to map to this, okay, yeah. And the X and Y can be computed, okay, by this formula. But then you have to compute the priority, okay, X plus Y mode 2. Okay, and then the X has to pass the priority, and then the I will be computed, yeah, as this. Okay, so from the IE, okay, from the even size index, and then I can get the full lattice size index. Okay, so for the odd size, okay, similarly, okay, so the odd size index, okay. Then you can also get the XY and then the full index. Okay. So so this is the even size to the full space and the odd space from the even space to the odd space full space, and then also from the odd space to the full space. Okay. So this is the code. Okay. Now, so the even size IE, okay, because it's 16 by 16. So the for even size only half of the index from 0 to 7. Similar for the odd is the 0 to 7. Okay. And with this conversion, okay, I can map the IE number to the XY and then to the I. And this I, okay, is the index on the full lattice. Okay. And similarly for the odd side here, okay, I can map this to the full index, okay, the side index on the full lattice. Okay. So just by this code, okay, and this code is exactly the same here. Okay. Okay. Yeah, you can think about this, and then I think it's easy to figure out why this works. Okay. So yeah. So anyway, this is the code. Okay, and is available in this index even odd. Once we know how to do the even side and odd side, update them separately. Okay, then we can use the CUDA, okay, to do the simulation of the Ising model. Okay? Yeah. So that means I have to update the even side first. Okay. So I have to go through all the even size and then mapping the even size to the full index coordinate, and then the priority index. And then the rest is the same as before. Okay. So once you map the index, okay, to the full lattice size index, then the simulation here, you can compute everything, okay, as same as before. And then after updating the even size, then I updating the odd size. Okay, yeah, updating the spin on the odd size. Okay, so this is the yeah, CPU code. Okay, is the here. Okay, okay. So this is the updating with the even odd scheme. Okay, yeah, and both cases with the CPU code. Okay. Then the next time I will talk about how can I implement this with the global memory. Okay. Yeah. I think I have to stop at this point. Yeah, because now it's yeah. Okay. And I will continue next time. We will continue next time. So, any questions? Yeah. No.
So far, so good.
Okay. Okay. Great.
Right.
Okay. Yeah. Please go to a code and then read the code and then test one it. Okay. And see if you have any questions. Let me know. Okay. Yeah. Okay. Yeah. See you all next time. Okay.
Thank you very much.
Okay. Bye-bye.
Bye-bye.